Okay. Oh no, I've split it. Oh no. Good start. Alright, welcome to the standard content. So this is going to, well, we're going to start looking at the normal distribution. Now that's actually the title of the topic, but we're kind of going to be using the concept of a normal distribution, and I'll explain what that is in a sec, throughout the whole topic. So this is actually a year 12 thing in standard, and it does appear surface level that it's going to be, or that we're going to be looking at data, but it's not the data that you're used to. Like what you've seen in data is pretty much just like, oh, here's a million scores, now I put in my stem and leaf plot and I'm happy. Like it's not like that anymore. We're going a little bit further into it and a little bit more into the algebra, but not too far. But yeah, it's not as simple as like a list of scores and then graphing them and here's a list of scores, putting the calculator into what the mean is. Like stuff like that we're kind of moving away from, but we are moving towards looking at why we even care about the standard deviation, because I remember in class we were talking about it and talking about how it was a measure of range and stuff like that, and it's like, why don't we just use the range? And I didn't really have an answer for you because I guess I had no further context in year 10. So in year 12 we can talk about a little bit more. Okay, so just a quick reminder, the standard deviation is, let's say you've got the mean, so I don't know, let's say I've got a set of data that's like 1 to 10 and the mean was like 5 or something. The standard deviation is a measure of how far away most of your scores are from the mean. So you might find that here the standard deviation is like 2 or something. That means most of the scores are within 2 of 5. So like 3 and 7. That means most of my scores are in here, 1 standard deviation away. And we're going to see this actually quite significantly in a second. So that's what the standard deviation is, the way you work it out, which you're not going to be expected to do here because it takes a while, but you essentially just use your calculator. I'm not sure if people remember how to do that, but that's how you would do it. Okay, so the normal distribution. Now, what that is when you have a set of data and you graph it, that's called a distribution. So you might have seen like a frequency histogram. I've got the height of a bunch of people. I record all of that. And this graph is a distribution. The way that that distribution is represented is via a frequency histogram. That music's very loud. Okay. So the way that you represent it is using a frequency histogram. That's just one example, but this is a distribution. Now, what you'll find is, so what a normal distribution is it's one where the mean, the median, and the mode, so the average, the middle score, and the most common score are all in the middle. So, and it looks like a bell curve. So you might recognize this, I guess, because you might have seen it before, but a bell curve, so just means your data kind of looks like this, like the middle of it is symmetric. There's a few different words to describe the distribution of it. It's not skewed. Yeah, I guess that's all I have to say about that. So that's a normal distribution. Now, the normal distribution is a perfect symmetry. So this isn't just like, oh, there's a few scores here, or one big score there, and then like heaps here, and it kind of looks symmetric. No, a normal distribution is 100% symmetric. Now, a question has to tell you that it's a normal distribution. So you're going to get told, okay, here's a set of data. It is normally distributed. So you don't have to verify that it is. It's just worth noting that that's what it is. It's perfectly symmetric, and a question should give you that. Now, you might think that's kind of unrealistic. What kind of set of data is going to be perfectly symmetrical? Well, okay, that's a fair point. There's a couple of things I guess we can talk about. The first thing is norm. So when we look at data like in junior school and stuff, you might have like 10 scores, and then you might find that the mean, the median, and the mode are all the same, and you're like, oh, that kind of looks like a bell curve. And that's because you've only got 10 scores. If you had a larger sample size, then you're more likely going to get towards a normal distribution. So you think of the heights here. If I took the heights of everyone in our class, it'd be much more jaggedy, kind of like this, right? Whereas the more scores you take, the more it looks like my normal curve. So I guess if I were to take the heights of every single person in Australia, you might find that it looks pretty close to a normal curve. And there's a few examples here, like blood pressure and skull width is a very extreme example. I don't know why that's weird, but normal distributions. And a lot of time, people that run exams and stuff, they fix scores so that they fit a normal distribution. So in other words, if there's too many scores over here, they'll scale them so that they're more here, so that they look like a normal distribution. That's how scaling works. So I don't know if you've heard that, oh, maybe my mark will get scaled. That's what that means. Because if there's too many scores here and there's like one score here, they'll scale all these so they fit more towards a normal distribution. So that's what scaling actually is. Anyway, that's a lot of talk. I'm not actually going to answer any questions today. I'm just for this lesson, I'm just going to kind of cover what the normal distribution is. The third example is one of these things. So if you look in the top corner of the screen here, I'm not going to try and pronounce that because I don't want to accidentally swear or something. But this is just like a ball starts at the top here. So the ball starts at the top, and then it bounces off each of these, and it has a 50% chance of going left or right. So if you watch this one, it's got a 50% chance of going left or right. And this is a real thing. So people have made these with like sand and stuff, and then they just pour a bunch of sand in it. And what you'll find is with a large enough sample size, the distribution at the bottom will end up normal. So it'll look like a bell curve. It'll look like this standard normal distribution. And you can see that this low sample size right here, that doesn't look normally distributed at all. And that would be kind of the stuff that we've already experienced, like in class, like when I put 10 scores on the board and try and graph it, it's not normally normal. But if I do this for a long period of time, then it might be. So I'm just going to leave this in the top corner. Hopefully it's not too distracting. I'm going to record the next video, and I'll also have this in the background while doing that, so we can see if that kind of looks normally distributed by the end of those. So that's going to be there. So back to this. There is something called the empirical rule. So this is the only thing we're going to cover today. And it's, let's suppose I've got a normal curve. So I've got my normal curve. If I found the mean and the standard deviation, so just keep in mind, so up here, the mean would be in the middle. Okay, 50% of the scores would be on the left side of the mean, 50% of the scores would be on the right side of the mean. I hope that makes sense, because if the median's here, that's the middle score. So half of them are over here, half of them are over here. So that's my normal distribution. Now, if I were to find the standard deviation, so if you just think about what I had before, so remember how I had like 1 to 10, and I said 5, and I was like, okay, what if my standard deviation was 2? Then that would suggest that most of my scores are within 2 of 5. So that means most of my scores are in here. So most of them are going to be in here. So that's almost like what a box plot is. You know how you find the inner quartile range? That means like exactly 50% of the scores in here, and that uses the interquartile range. Here we're using the standard deviation. So standard deviation, that means most of the scores are in here. Actually, it's not just most, it's exactly 68% of the scores. So if I've got a normal distribution, I have my mean in the middle. So my mean here is x with a line on the top. That just means mean. Okay. So let's put that in. So that's my mean. If I went one standard deviation this way, so one standard deviation that way, and one standard deviation this way, okay, that would mean that 68% of my scores are within there. So if I were to look at this thing over here that I've got in the top corner, let's suppose the standard deviation's like 1, then you can see here quite simply the mean kind of looks like 3, right? So a standard deviation away from 3 would be 2 and 4. So that means here, that would be 68% of all the scores. So these three, these 3 bars would be around about 68% of the scores. So that's what that means. And if I went 2 standard deviations across, so x bar, if I went 1, 2, so plus a standard deviation, plus a standard deviation, and minus a standard deviation, and minus a standard deviation, then there would be 95% of all the scores. So if I have a normal distribution, most of my scores, in other words, 95% of them are going to be within 2 standard deviations. So yeah. And if I went 3 standard deviations, which is pretty far, I'm going to have pretty much all of them. So 99.7%. So in other words, if I measured everyone's heights, so like this, okay, you might find that the median's 170 or the mean's 170. Maybe the standard deviation's 10. So maybe this is like 160, maybe this is 150, maybe this is 140, right? Okay, so that's 1 standard deviation. So that means 68% of people are going to be between 160 centimeters and 180 centimeters. That would mean that 95% are going to be 2 standard deviations away, So in other words, 150 centimeters to 190 centimeters, that would be around about 95%. And then if I went 3 standard deviations away, that means that there'd be 99.7% of people would be between 140 centimeters and 200 centimeters. And that kind of makes sense because if I went like further, if I went to 210 centimeters, not that many people that are 2 meters and 10 centimeters. In fact, that would be less than 0.3 or half of that of the population. Anyway, I hope that kind of makes some sense. So if I've got a normal distribution, if I start moving standard deviations away, I can tell you specifically what percentage of people are within those standard deviations. And the last one, this is just a thing that kind of shows you all of it together. So 1 standard deviation away, 68%. 2 standard deviations away, and it's down here, 95% and 99.7%. So I just want you to be able to identify the percentages within a normal distribution. So just remember, you'd be given the fact. So a question would probably say, here's a normal distribution, here's the mean, here's the standard deviation. Tell me what 2 scores are 68% of the people. I don't know, something like that. So if I said, all right, well, let's just make up some example. If I said the mean, or X bar, is, let's use that line example. So let's go with this, 1 and 10. If I said the mean was 5, and I said the standard deviation was 2, which is what I was saying before, then what percentage of people, or actually scores, are between 3 and 7? Well, I know that 3 is here and 7 is here, and that's a standard deviation away from the mean. That means that 68% of the scores are within here. So that means equals 68% of the scores. I hope that kind of makes sense. Anyway, that's it. So that's all I really want you to know. That's called the empirical rule. Actually, it used to, before I end that, it used to be called the 68, 95, 99.7 rule. I wonder why it was called that. But now it's called